Good morning, everyone. Thank you for joining my presentations. This topic is a conceptual design of a pre-stressed concrete spar floater supporting a 10 MW offshore wind turbine. I'm Wichuda, a Ph.D. candidate from Yokohama National University, Japan, presenter and author. Co-authors are Mr. Han-sang, Dr. Mortar, Professor Gonsalves, Professor Fujiyama, and Professor Maekawa. This presentation includes introduction and background of the study, research objective, research methodology, results and discussion, and the final is conclusion. In 2019, Japan implemented a new law to promote offshore wind, enabling offshore wind farms to be operated by local and foreign companies along Japanese coastal waters around 30,000 kilometers. However, greater than 90% of Japan's annual wind energy generation potential locates in the deep ocean. That will require floating platform technologies. Among other floating platform concepts, a gravity-based spar platform exhibits small heave motions because of the deep draft. This is advantageous for power take-off cables, umbilicals, and mooring systems. The deep draft means that it cannot be used in shallow waters. However, the simple cylindrical shape of the spar-based concept has been shown to achieve the cost reductions. In Japan, 2012, a half-scale model spar mounted with a 100 kW wind turbine was installed at Goto Island, Nagasaki Prefecture, and after that, in April 2016, a full-size 2 MW wind turbine was installed at the same location after the previous one was removed. Both spars were hybrid structures. The upper part made from steel and the lower part made from prestressed concrete. In 2014, the Fukushima Forward project failed to construct the 7 MW advanced spar made from steel. When we talk about the steel platform, the decreasing of fatigue life because corrosion in the connection joints is one of a crucial concern, and as a result, concrete materials have been increasingly used to develop offshore substructures because of their advantageous properties. Most research has studied the use of reinforced or prestressed concrete. However, the use of precast segments prestressed concrete has not been widely investigated. The objective of this research is therefore to develop a concrete spar supporting a 10 MW offshore wind turbine using precast segments prestressed by a post-tensioning system. Here are the advantages of this approach. The concrete segments can be cast at any place before being transported to the fabrication site. The unbound post-tensioning system is chosen to connect the precast segments because this method eliminates grouting operation, addressing the economic aspect of this study. The pre-compression induced by prestressing force through the tendons considerably increase the external force required to crack the concrete. This prevents the corrosion due to chloride ion transport through water penetration to the reinforcing bar. In addition, unlike steel fabrication, the production of precast concrete segments does not require highly skilled labor. Workers in any local communities can do this job. In this study, the analysis was performed into two parts. First is parametric stability and motion analysis to define the geometry of the spar. The structural response under wave action will be evaluated by WAMIT. The coupled dynamic analysis of the system will be performed by OpenFAST. Second is finite element analysis to investigate the nonlinear behavior of the concrete structure, which will be performed by finite element code COM3 developed by Professor Maekawa. The IEA 10 MW was used as the reference wind turbine in this study. The wave condition from locations around the Japanese Sea performed in three conditions: operational, storm, and centenary, and they are described by the ISSC wave spectrum. Three wind conditions were performed with irregular waves, maximum operation, cutout wind speed, and typhoon conditions. This slide shows the sensitivity analysis to get the first trial geometry shape of the spar. At first, the spar was defined to achieve hydrostatic stability without considering the mooring system. The valid were placed above seawater for workability viewpoint and investigate the effects of fatigue life compared to the use of mooring lines below seawater in the future study. The spar was defined using 11 parameters in the parametric analysis. Parameter A, D, and E were modified to achieve a feasible geometry. Parameter D is a spar diameter, and it was varied from 12 to 24 meters. Parameter E is hull thickness, and it was varied from 0.45 to 0.85 meters. Consider the appropriate thickness of prestressed concrete. The results indicate that a spar diameter 18, hull thickness 0.45 and draft 123 satisfy the intact stability criteria, which will be used in the next analysis. The trial geometry was modeled, including the mooring lines and the reference wind turbine, using the tool named H2X to compute static equilibrium. At the static equilibrium, we found that the spar diameter D needs to be adjusted to 17 meters, the hull thickness E to 0.6 meters, and the final required draft was 120. These hydrostatic properties were then applied to vomit and open fast for the coupled dynamic analysis. In order to validate the open fast model under wave conditions, RAO results from open fast were compared to the vomit under the condition with wave but no wind. The results show good agreement in terms of surge and heave motions. However, the coupled dynamic response of the wind turbine control system servo-didn't magnify the pitch motions. And also, the RAOs show that the natural period of the spar was out of the range of the ocean wave, except for the heave motion, which is around 22 seconds. However, this is beyond the range of the installation location considered in this study. Therefore, we could imply that the proposed spar can avoid structural resonance induced by wave excitations. To confirm this behavior, a spectral analysis of rigid body motions was then conducted. Here are the results at storm conditions presented together with the input wave spectrum. We can see that the significant response motions are much smaller than the input wave energies, confirming that the structure would not have resonance induced by wave excitation. In open fast calculation, the results show that wind turbine operation increase or significant motions of the platform, particularly the pitch motions. Therefore, the wind effects must be investigated in the future study. This is a full scale of the country finite element model. It is composed of around 17,600 elements and 25,600 nodes. As this conceptual design was developed based on the economic aspect, therefore, all concrete parts are regular concrete with the compressive strength 41 megapascal. The reinforcement ratio was approximated using the initial design estimation, considering the requirements of each part. The static loads applied to concrete finite element model were obtained from the most dominant case of open fast analysis. The results show that the highest force occurs under the rate wind speed in storm conditions. Therefore, it is considered as the dominant case for investigate stress and strain distributions. This force were applied at the bottom of the steel tower and valid connections as 20 time step monotonic static loads. These connections were placed above seawater. Therefore, in this study, the hydrodynamic pressure was not considered in the finite element analysis. Here we can see strain and strain localization without considering the precessing force. Figure A shows the principal strain. The red color means the strain in concrete is over than 200 microstrains, or ultimate tensile strains. At this point, microcracks start to generate. Therefore, The red area is the critical area for designing precessing force. Figure B shows the principal tensile stress. The red color means tensile stress was higher than the concrete tensile capacity. In this case, the stress can still be transferred by the reinforcing bar because it remains within the elastic range of the steel material. However, in plain concrete with no reinforcements, the stress will be transferred only by concrete. Figure C shows the principal compressive stress. It was mostly less than the compressive strength considered in this study, except at the embedded part of the mooring connections and some parts of the hull. Therefore, the use of a higher concrete compressive strength may be preferable in future design. Based on the study results, the conclusion can be drawn that the proposed bar can be applied to support a reference wind turbine, confirmed by spectral analysis, which show low significant response motions. The impact of the wind turbine operation increased or significant motions of the platform, particularly the pitch motion. The wind effects must therefore be included in the future spar design optimization process. Average wind speed under the storm conditions, where wave has highest energy, can be considered the dominant case in the design of the floater. The concrete finite element analysis results show the highest stress and stress concentrations in the steel concrete connection parts because of the large deformations of the elements there. Concrete strain that is over the ultimate concrete tensile strain indicate the critical area for designing the precessing force. The concrete compressive stress was still close to the compressive capacity of the normal strain concrete. However, some has exceeded the limit. High-strength concrete is preferable for future design. In this study, the alternative concrete to steel floater, assuming future mass product, was successfully demonstrated. In the future, the dynamic response in time domain of force and hydrodynamic pressure will be applied to the finite element analysis. Structural and connection design of the proposed concrete spar will be performed. The effects of wind turbine operation on pitch motions will be investigated. The spar model test and steel concrete connections fatigue test will be conducted. And this is all of my presentations today. Thank you very much for your attention.